Good day. Today, we will talk about our new topic in our subject, and today's lesson will be about recursion. For this chapter, we will talk about the following topics. We will talk about recursive functions for tasks, recursive functions for values, and thinking recursively. Before anything else, let's first talk about recursive functions for tasks. In this section, we will be talking about the basics of recursive functions. But first, let's first define what a recursive function is. Basically, a recursive function is a function which contains a call to itself. So basically, a recursive function is a function which calls itself. When we break a task into smaller tasks, it may be that the subtask is a smaller example of the same task. For example, we would like to search an array, which could be divided into searching the first and second halves of the array. Thus, searching each half is a smaller version of searching the whole array, which would make the task simpler. Tasks like this can be solved with recursive functions, in which a bigger task is subdivided into a smaller task which is exactly the same version of the main task. Let's have our first example. For instance, we have the following problem. We would like to write a number one digit at a time on separate lines. Thus, we can have the following function declaration. The condition is that the number could be greater or equal to 0, and of course, the post condition is that the number will be written to the screen vertically with each digit on a separate line. How are we going to design the algorithm? In its simplest case, if n is one digit long, we can simply write the number. On the other hand, we can also output all but the last digit vertically. Then we can write the last digit. Step 1 is a smaller version of the original task. And step 2 is the simplest case, whereas we're only going to write the last digit. Now that we have a grasp of what our solution will be, we can now write the following algorithm. For example, we are going to call our function writeVertical. This is how our algorithm will look like. For instance, if the number is less than 10, then it means that we only have a single digit to print. Otherwise, we will call a recursive function. In this case, we will recursively call our function writeVertical until such time that a certain condition is met, which will end our recursive call. Now that we have formulated our algorithm, we can now translate that into an actual pseudocode in C++. For instance, we have the following, which would return n with the last digit removed. For instance, 124 over 10 would give us 12. We are also going to need the following equation. For instance, n modulo 10 would return the last digit of n. For instance, 124 modulo 10 would give us 4. At this point, we now have a picture of how our recursive function would work and how it's going to print our number one digit per line. Removing the first digit would be just as valid for defining a recursive solution. And it would be more difficult to translate into C++. So if we're going to translate this into an actual C++ code, our first example would look like this way. In our main function, we can see here that we are calling our recursive function in 3 different ways, and for each call, it is given different inputs. If we are going to take a look inside our function definition, this is how it's going to look like. And if you will notice, this is the part where our function right vertical is calling itself. If we are going to run this function, this is how it would look like. As we can see here, we called our recursive function 3 times, and for each call, we provided it with different inputs. And as we can see here, whatever our input was, each digit was written on the screen one line at a time. To have a clearer view of what happened, it makes sense that we make a trace of our recursive call. For example, let's take a look at this particular call where we used 123 as input. Looking back at our algorithm, we are going to check if our input is a single digit, and if so, it will print our number right away. Otherwise, if it has more than 2 digits, it is going to perform this recursive call. For instance, 123 will be divided to 10, and of course, we will also have 123 modulo 10. But of course, it will not output this right away, because as we can see here, our recursive call is not yet done. So let's continue our trace. Now, if we are going to perform this 123 over 10, this will now give us the following scenario. Our input to our next recursive call would be 12. And if we're going to take a look at this, whatever is the result of this will be stored to a temporary storage. And then the recursive call continues. Now we are left with the value 12, which will be used as input for the next recursive call. For our second recursive call, we now have the following scenario. As you can see here, the new value for our input is now 12. Still, the first condition will not be executed since we still have a double-digit number. Therefore, we will proceed on the next statement, which would again perform a recursive call to our function, which will now give us 12 over 10. And of course, whatever is the result of this statement, 12 modulo 10, will again be placed in our temporary storage. Continuing, we are now left with 1, since 12 over 10 will give us a result of 1. Now, we now have the final scenario. As we can see here, our last recursive call will now give us an input of 1, which would make the first statement true. Therefore, it will proceed with displaying the final value of our input, which is 1. And looking back at our previous output that was temporarily stored, it is now time for them to be retrieved, for them to be displayed on the screen as our final output. In this case, the simplest case has now been reached. Therefore, it will be the end of our recursive call, which will give us an output of 1, and it will end the function call. If we will take a closer look at our recursion, there were no new keywords used. What happened is it simply called itself with a different argument for each iteration or recursive call. Of course, our recursive calls are tracked by first temporarily stopping execution at the recursive call, and the result of the call is needed before proceeding. And as what we have seen a while ago, we need to save information from our current execution or recursive call, which will be used later as we retrieve our final output. So, how does recursion ends? Eventually, one of the recursive calls must not depend on another recursive call. Recursive functions are defined as one or more cases where the task is accomplished by using recursive calls to do a smaller version of the task. As we have seen a while ago, we performed a task by subdividing it into recursive calls. As we can see, for each recursive call, an output for the said task has been produced and stored temporarily until such time that a certain condition was met, which would end our recursive call, which in turn would retrieve the output that we have temporarily stored, and therefore will comprise the final set of outputs that will be shown in our screen. One or more cases where the task is accomplished without the use of any recursive call is called the base case or stopping cases. In the case of our example a while ago, when the condition is met wherein our output is 1, that would be the condition which would end our recursive call. There's also such thing called infinite recursion. It is a function that never reaches a base case and in theory will run forever. In practice, the computer will run out of resources and the program will terminate abnormally. Here's an example of an infinite recursion. For example, we have the same function name, but without the base case. As we can see here, this will eventually call right vertical with an argument of 0, and of course, it will keep on calling the same function with the same argument, and of course, it will never end. On the other hand, computers use a structure called a stack to keep track of recursion. If we will recall a while ago, we've already mentioned that the output of each recursive call is stored in a temporary storage. Actually, that storage is called a stack. A stack is a memory structure which is analogous to a stack of paper. How does it work? To place information on the stack, write it on a piece of paper and place it on top of the stack. To place more information on the stack, we use another sheet of paper to write information and place it on top of the stack. To retrieve information, we can only do so by accessing the topmost sheet of paper, which can be read and thrown away when it is no longer needed. By principle, we access information or data from our stack using the last in, first out principle. Thus, a stack is a last in, first out memory structure. The last item placed is the first that can be removed. Whenever a function is called, the computer uses a clean sheet of paper, or in this case, a new memory address where the new data can be stored. In this case, the function definition is copied to the paper, or shall we say, to that memory location. Then the arguments are plugged in for the parameters. Then the computer starts to execute the function body. So how do stacks and the recursive call relate with each other? When execution of a function definition reaches a recursive call, the execution stops. Then, information is saved on a clean sheet of paper or to a new memory location to enable resumption of execution later, thus allowing us to retrieve our previous output. By principle, this sheet of paper is placed on top of the stack, thus following the last in, first out principle of the stack data structure. Then, a new sheet is used for the recursive call. In this case, a new function definition is written and arguments are plugged into parameters. Then, the execution of the recursive call begins. Then, what happens to the stack when we reach the ending of our recursive calls? When a recursive call function is able to complete its computation with no recursive calls, the computer retrieves the top sheet of paper or the top of our stack and resumes computation based on the information on the sheet. When that computation ends, that sheet of paper or memory space is discarded and the next sheet of paper on the stack is retrieved so that processing can resume. This process will keep on until no sheets remain in the stack, which means all of the data that has been temporarily stored has now been fully retrieved. Thus, the end of our recursive call. Of course, the computer does not use paper. What we are referring to actually, in terms of data storage, are the memory space or the memory location in our computer. The contents of those portions of memory is what we call an activation frame. The activation frame does not actually contain a copy of the function definition, but references a single copy of the function, which contains whatever argument that was used in that call, as well as the output that has been produced. We also have a phenomenon called stack overflow, which we encounter when we are dealing with recursive functions. Because each recursive call causes an activation frame to be placed on the stack, infinite recursion can force the stack to grow beyond its limits to accommodate all the activation frames required. Thus, it would result to a stack overflow. A stack overflow causes abnormal termination of a program. In other words, this would cause our program to crash. Now, we will compare recursion and iteration. If we will recall, any task that can be accomplished using recursion can also be done without recursion, which means we can always create another version of our recursive function, and that is by the use of iteration. A non-recursive version of a function typically contains a loop or loops. Also, a non-recursive version of a function is usually called an iterative version, thus giving us a recursive or iterative version of a function. Of course, when we are dealing with a recursive function, it is said that it usually runs slower. It also uses more storage and may use code that is easier to write and understand. If we will recall and take a look at the first example of a recursive function that we wrote, the code actually looks straightforward, and of course it is much shorter as compared with its iterative counterpart. Here's an example. This is the same function that we wrote in our first example, and as you can see here, we have the same function name, the same set of arguments, and basically it performs the same task. But in this case, we are no longer using recursion. Instead, we are now using iteration, which involves loops. As we can see here, we actually used two kinds of loop, a while loop and a for loop. Eventually, this would accomplish the same thing as its recursive counterpart.